Good afternoon. My name is Davis Lambert. I will be TM on behalf of John Menard today. First, we're going to be starting with our tabletop question, which is for Alec Rosas. So, Alec, come on up. So, John's question is, one of Hollywood's favorite movie plots involves robots taking over the world. In your own words, do you believe that artificial intelligence will evolve to the point where robots will be capable of developing the skills needed in order to take over the world?
So this is actually kind of a fear of mine, almost irrationally. So my dad told me yesterday that there was a Disney cruise that they just made, no, a Carnival cruise that they just made where the bar is like 3 stories high and it's completely run by robots, and the robots can go up and down and they pour you a drink and then you get your drink. So that's just a start. Once one company does it, it's expensive now, but eventually they'll make it inexpensive, and then all of a sudden it'll be the better way, and then our kids could possibly ask us what it was like to have a person serve you a drink. And so then you get to the point where it starts to develop, and you teach it to learn. You teach it to, this happened, this was a mistake, now push this out. And so then basically teach it to rationalize through things. And I mean, really, I'm afraid that they'd get so smart that they'd realize that humans are they poorly take care of the home that they live in, and they rationalize us as a problem, and then destroy us and say, well, we'll take care of this earth better, and we'll do this for them. And so then, yes, I do think it's possible, especially the rate that a computer grew. I mean, a computer used to be the size of a room. What was that, like 20, 30 years ago? If that. And now it's like, can be this small. So I mean, if you have now robots that look like humans, some of them literally look like humans. You have robots that can serve you drinks, then give it 10 more years, and robots will be able to think. And I don't think they're gonna like humans very much. I think humans will be mean to robots and stuff like that. I don't know. So that's it. That's what I think.
Thank you very much, Alec. Next, we will be having Tyler Smith to talk about the report from last week.
Process. I had experiment 1, so I'm the reporter for it. It was the steam ejector experiment. The 4 objectives were to calculate the steam flow rate through a chug nozzle, investigate the efficiency of the ejector as a water heater and as a pump, and then to perform an overall mass and energy balance on the ejector. The main portion of the entire apparatus was the ejector that was just mentioned 4 times in those objectives. This is the first part of it. This is just a graph or a schematic showing. Come on. Where is it? All right. For flow that is supersonic, you need a converging and diverging nozzle. This is just that. It comes in at a high pressure, low velocity, and it reaches a choking point of the throat, and then it expands. And then what we do with that, combine it with, it's got a little bit of a vacuum on the backside where it's expanding, and then we suction the water from a different tank through there, heat it up, and it's used to heat and pump water. I'm really flustered because this experiment absolutely tore me up. This is what it looks like. This is the entire schematic of the thing. Steam valve, temperature and pressure gauges, here, and right there for the coming in and going out and the suction water. The data that we got, trial 1, we measured from 24 to 30 centimeters. It was 143 degrees Celsius and 3 bar, and those 2 and 3 represent the numbers that come with it on the schematic. 37 degrees Celsius and 0.2 bar going out, and then 26 degrees Celsius and negative 0.16 bar, which represent the fact that it's getting suctioned up and from the tank into the ejector. Trial 2, they would basically stay the same. The temperature went up a little bit, the pressure went up a little bit, and it affected the outgoing pressure and temperature. We did the same thing again, we just kept going higher and higher. Got all that data, and then you're supposed to do a mass balance, an energy balance, and entropy analysis. These are just equations showing what I would have done. I'm not going to go through the actual analysis that I did because it was very extensive and difficult, and I probably didn't do it right. So we're just going to stick with these nice images, which I grabbed from these links, so I'm not plagiarizing. Just standard stuff, we've all done this before, mass balance, energy balance. Entropy analysis, something typically teachers let us get away with just ignoring, but I believe I was doing it, I was messing around with that so I could get efficiencies. And that, I'm going to get onto this slide because this slide I actually thought was interesting. I learned something from this experiment. I've never heard of second law efficiency ever. I've written on here, yeah. Second law efficiency. So there are two kinds of efficiencies. The first law efficiency and the second law efficiency. First law is kind of what you think it would be. It's just how well it would work. Second law efficiency, again, assuming I did this correctly and got my information right, is this is the maximum something can work for the heat engine. So how does it work against that? It's not just how well does it work, how well does it work against the best we can possibly do. Thought that was cool, but it was also really difficult to calculate. So, what is this? Come on. That should be in there. That's weird. It's steam C. I put steam C. All right, let's go over here. Inlet pressure. So this shows the mass flow rate of the liquid, steam at A and steam at B against the inlet pressure and the outlet pressure. So to show you what I mean by steam A and steam B real quick, steam A and steam B, I did A, B, C. Should have signified that a little better. But as you can see, the blue line is whenever we, come on, this is killing me. I'm doing so poorly. We actually had like the site last week. Like, we looked at it, we had Eric sit there with the timer and he said he stopped the timer. That's why that's erratic. Yellow, the pressure and temperature went up pretty steadily with how we changed the knobs. And you can see yellow kind of goes along with that. It's what would be expected. Blue goes up and then it's negative, which makes absolutely no sense. But I left it in as negative because I think it actually, and that measuring point in particular, I thought was interesting because if you knock off half a second from the time, which considering Eric's sitting there and when Alec tells him, hey, stop it, he stops it, it's about half a second and it changed, and it would have made it positive as opposed to negative, which again is kind of ridiculous measurement. So just going with the empirical data and the gauges that are made to measure these things as opposed to us manually doing it, you get a lot more consistent data that's a lot more appropriate. The liquid, by comparison to the steam, stayed roughly even. That's why it's flat right there and there. Steam C. Okay, that was, let's just stay with what I know. Efficiency. On the efficiencies. So basically, again, I thought this was fascinating. I'm probably nerding out in a weird way. But the green bars are going to be the first law efficiencies and the blue bars the second law efficiencies. So the green bars, they're not horrendously efficient. I've got numbers like 26 and 23 and 17 for as far as a heater, but it's 90 and 92 and 68 compared to second law efficiency. So it didn't do great, but compared to what is possible, it was pretty gosh darn efficient for a water heater. Pump is not much better. It's 28, 20, and 15, and it's only 34, 26, and 19 on second law. And then combined, again, wasn't given an equation, so I just averaged them out, and it's going to be 27, 22, and 16, and they're a lot lower, which stands to reason, because it's an average of the two. You got really high on the water heater, really low on the pump. Conclusion, and this is what really threw me off because it didn't feel right. As the pressure went up, temperature went up, mass flow rate went up. That makes sense. But the efficiency also went up, and I really feel like I shouldn't be saying any of this in the presentation, but I'm trying to learn. So I don't think it should have gone up. I was talking about it with Eric before I gave this presentation. He gave me a funny look. I got efficiency went up. Efficiency went up. This is trial 1, 2, 3, 1, 2, 3, all the way up. And again, we upped the pressure and temperature every single time, and the efficiency kept going up. I thought it was weird. Maybe that's right, and I just don't know things. But that's my conclusion. And up next, Toastmaster. I'm not good with that. Anyway.
Thank you, Tyler. Up next, we have Eric Rowley to talk about next week's lab, the bomb calorimetry.
Okay, so as Davis mentioned, next week we are doing bomb calorimetry. So just for the purpose of this presentation, I'm just going to introduce what calorimeter is, talk a little bit about the apparatus that can be found to my right, y'all's left, and then state the goals and theory behind how this lab works before I get to my ultimate predictions. So to introduce it, calorimetry, as this dictionary definition points out, is simply a measurement of the amount of heat released or absorbed in a chemical reaction, a change of state, or formation of solution. Now this textbook definition, scientists like it. Practical application, we've all seen this label. And the calories on this label have to do with the calorimetry of an object. You burn it, and it gives off this much heat. So it's telling you how much heat is in the food or drink item that you're about to consume. The apparatus is the Par Oxygen Bomb Calorimeter. It is highly used all throughout science, one of the most common ways to do calorimetry. And there's two main parts. You have the calorimeter itself, which is made out of a known material. The manual said to assume steel. And you place a known amount of water inside. There's a stirrer that stirs the water around to make sure that the heat gets dispersed about as well as it can. And then inside the calorimeter, you put the bomb. The bomb has all of these parts. You're putting your fuel in, which we will be using benzoic acid as the test run, and then an unknown fuel later on. And you run in an ignition wire through which a current's going to go through and ignite the object, henceforth why it's called a bomb. So the goals of this lab are simply to find the thermal capacitance in the calorimeter. I'll get to what that means in a second. And also to find the gross heat of combustion of an unknown sample. We're using benzoic acid, which has a known heat of combustion, so we can compare how the benzoic acid ignites versus how it's supposed to ignite, and then adjust our results to compensate for whatever the unknown fuel is going to be. So the theory behind this simple equation: heat equals mass times specific heat times change in temperature. Change in temperature, delta T, we should know that by now. Heat, you should also know that by now. But this MCV is what's known as thermal capacitance. So this, if you remember from system dynamics, we assign capacitances and resistances and inductances to just seemingly random things. Well, this one goes to capacitance. And we can figure this out using the benzoic acid. So the predictions for this lab: well, the system thermal capacitance, using steel and the known amount of water, should come out to somewhere around 13.5 joules per gram Kelvin. The ignition fuel, benzoic acid, when we ignite it, it should give us about 2 kelvins in temperature change. As for the heat of combustion of the unknown sample, well, that's obviously unknown. I don't know what we're putting in there. But there are ways that we could estimate this. If we're using a food item, like I believe we're supposed to be doing for this lab, then you can look at the packaging and just see, all right, this has 200 calories, so it should put out 200 calories of heat. If we're using an organic sample, they have all kinds of different tabulated values on the chart. I know I used it in my advanced high school chemistry class. Don't remember much of it, but the charts do exist. So that's basically it, and I'll give it back to Davis to conclude.
Thank you, Eric. So that concludes today's presentations, and next week we'll be moving